Okay, we're gonna talk about an application of equilibrium. So we're gonna learn about acids and bases and the equilibrium that they have in water. Okay. So we'll probably do this chapter in a couple lectures because it's kind of long. So aqueous equilibrium. So we're going to talk about equilibrium in solutions of water as the solvent. We're going to talk about acids and bases. And so we're going to define what that means to say something's an acid or a base. So there are several definitions for acids and bases. An Arrhenius acid is a substance that dissociates in water to produce hydrogen ions, H+. So anything that breaks apart to make H+ and something else. And then an Arrhenius base is a substance that dissociates in water to produce hydroxide ions, which are OH-. So the M could be something like lithium hydroxide. Any hydroxide will dissociate to form M+, whatever the cation is, and then the hydroxide ion, which makes it a base. So the definition that we're going to use for acids and bases is a little more general, and it's going to be the Bronsted-Lowry theory. So these are very subtle differences in the definitions, but they'll be important to us. So a Bronsted-Lowry acid is a substance that can transfer hydrogen ions, in other words, a proton donor. And a Bronsted-Lowry base is a substance that can accept hydrogen ions, H+, in other words, a proton acceptor. So that's slightly different definition than our Arrhenius, where in each case, an acid could dissociate to make H+, a base could dissociate to make OH-. You're going to have similar properties, but we'll see these definitions are just a little bit different. So in this case, the HA is the proton donor. The B in this case is a H+ acceptor, so that makes it a base. And so if the proton goes from HA over to the B, then we have now a new acid on that side, pardon me, BH+, and then we have a new base on the other side. The H has left the A, and now we have A-. So when you look at this, you essentially have acid-base pairs. So they're called conjugate acid-base pairs. So the lines connect those. So HA gives up a proton to become A-. And so when it has the proton, it's an acid. And when it doesn't have the proton, it's a base. So the acid can donate the proton and the base can accept a proton. Same thing with the B, but now B is a base when it's on the reactant side, and it can accept an H+. And then when it's accepted the H+ on the product side, it's become an acid. So there are chemical species whose formulas differ by only one hydrogen ion. Those are acid-base conjugate pairs. Excuse me. So as we talk about acid dissociation equilibrium, we're going to talk about it in water. So if we have an acid such as HA on the bottom line here, the base will be the water itself, our liquid, and the water can pick up a proton, so that makes it a base, and the HA, whatever our acid is, can give a proton to water. So we create the hydronium cation and leave behind a base. Base dissociation is similar, but now it's not necessarily dissociating. NH3, ammonia, is a base. And when you put it in water, it doesn't have any OH-, so it wouldn't be an Arrhenius base because it doesn't dissociate to make OH-, but it does accept a proton, which makes it a base, a Bronsted-Lowry base. So on the bottom line, it shows you that NH3 can pick up a proton off of water. So now water is acting as our acid. When when an acid was put into water, then the water acted as a base. But now when we put base into water, the water can also act like an acid. So it can pick up it can give up a proton to NH3, leaving behind OH-. So it's a different definition you're not dissociating to make the OH minus. It didn't come out of the NH3, but it reacted with water to make it. So the base is still something that's going to have OH minus and water. And now the new acid on the right-hand side is NH4 plus. The ammonia NH3 is a base. It accepts a proton. It becomes an acid NH4 plus. So when we talk about the relative strength, if you put an acid and a base together, they're only going to react if the acid is stronger on the reactant side. So with equal concentration of reactants and products, what will be the direction of the reaction? And that it will always be from the left-hand side, the stronger acid plus stronger base, going to a weaker acid plus weaker base. And so we can figure that out by knowing the properties of the acid as we go through. So an acid that's only partially dissociated in water and therefore is a weak electrolyte makes it a weak acid. So if you take HA, a weak acid, and you put it, well, this case, it's a strong acid. If you put it into water, then it will 100% dissociate. So you get a one-way street, and all of the HA becomes H3O plus and A minus. And showing you that barely any HA is left behind undissociated. That's a strong acid. But there are differing degrees of acidity. You also have acids where you put them into water and only some of the molecules dissociate. So some of them dissociate to make H3O plus and A minus. Those will always be the same height, the two blue bars, but some of it will be left behind. So this is a weaker acid than the one above it. And then the very weakest acid is the one at the bottom, which says barely any, about 0 dissociates. So every HA that you put into water pretty much stays together, and very, very few of them dissociate to make H3O plus and A minus. So 100% dissociation makes it a strong acid. Somewhere in between makes it a weak acid, and a very weak acid is essentially an HA that doesn't dissociate at all. So this is just a small table that tells us about the properties of a few acids and bases. So these top 4 acids are a few. There are, I think, only 6 strong acids, but each of these dissociates 100%. And then as you go down, they get weaker and weaker and weaker as acids, which means their conjugate bases get stronger. So if something doesn't want to give up a proton, that means that the conjugate base really wants to pick, or if it doesn't want to give up a proton, that means that its conjugate base really wants to pick up a proton. So the arrows go the opposite direction. So strong acid at the top, weaker acids at the bottom, and then it's going to be the inverse for their base. So the conjugate base of each of these, if it's a weak acid, it will be a very strong conjugate base, and vice versa. If HClO4, which is perchloric acid, really wants to 100% give up its proton, then if you have the anion in solution, it's not going to want to pick up a proton because the conjugate acid really wanted to dissociate. So the arrows go the opposite direction for acid strength and base strength for the acid-base conjugate pairs. And you'd always be given this information. So there are tables that we'll use that will help us understand the relative strength of acids, but you don't have to know if an acid is weak or strong. So hydrated protons and hydronium ions. So if you have HA and you are treating it as an Arrhenius acid, it can dissociate in water to make H plus and A minus. So it's an Arrhenius acid. But in reality, when you put hydrogen ions into solution, you're never going to see them floating around alone. They are very, very small, positively charged things. They have no electrons left if you take an electron off of a hydrogen atom. And therefore, when they run into water, they're going to essentially bond to that lone pair on the water molecule. And you get differing degrees of hydration, so differing degrees of water molecules associated with each H plus. But for our purposes, we'll just say H plus is equivalent to H3O plus, where you have H plus hydrated by 1 water molecule. But basically, it's just showing you a more realistic picture of what happens when you put H plus in water. H plus does not want to sit around alone. It's too small and positively charged, and it wants to share that charge with something else to make it less densely charged. So this is showing us some factors that affect acid strength. And we are actually going to skip this section till the end of the class after we've done our chapter on thermodynamics. So we won't do this section on acid strength until later. Okay, so water is very unique. We already saw that it can act as an acid or a base depending on what you put into it. But it's also true it can act as an acid and a base with itself. So water dissociates according to this first equation. If you have two water molecules, one of them can pick up a proton off of the other one. So you're making an H3O plus and an OH minus, leaving the other one as an OH minus. It doesn't happen very much, so it's a very, very small amount dissociates like this, but it happens enough that we know the concentration. So the Kw, which is just an equilibrium constant for this reaction. So if we look back at what we did in the last chapter, the equilibrium constant for the dissociation of water would be H3O plus times OH minus, and the water, because it's a liquid, would just be left out. So that's 1. So the equilibrium constant for this reaction would just be the hydronium ion times hydroxide ion concentration. And so at 25 degrees, the value for Kw is 1 times 10 to the minus 14. So it's a pretty small equilibrium constant. And as we know from last chapter, that means the reaction really doesn't take place with much significance. So that makes it that if you have pure water, you have a concentration of H3O plus and OH minus of 1 times 10 to the minus 7. And this just then allows you to calculate the concentration of each. So water dissociates, and therefore you can determine the concentration of OH minus and H3O plus using the Kw. So this is the dissociation of water. And if we look at pure water in the middle, the H3O plus and the OH minus will be equal to each other. Based on that reaction, has one of each as a product. But if we put some acid into our solution, for the far left, that means when you look at this equilibrium, then if H3O plus goes up, and this equilibrium constant has to stay constant at 1 times 10 to the minus 14, that means that the OH minus concentration has to go down. Same thing is true on the far right-hand side. If you put some base into the solution, then the OH minus is greater. And in order to keep the product with the hydronium ion concentration equal to the equilibrium constant, the H3O plus would have to go down. And that's just what these bars are showing. So if it's acidic, H3O plus is greater than OH minus. If it's neutral, they're equal to each other. And if it's basic, you have more OH minus than H3O plus in solution. And we start looking at these really tiny numbers like 10 to the minus 14, 10 to the minus 7, concentrations that are very small. We're going to change how we talk about the concentration of H3O plus and use something called the pH scale. So the P function is the negative log of anything. So right now we're talking about pH, P of the hydrogen ion concentration or the hydronium ion concentration. And so you're going to take the negative log of that concentration. So that will allow us to say, if we look back here, that when the solution is neutral, then the H3O plus concentration is 1 times 10 to the minus 7. If you take the negative log of that, you take the log and you get minus 7. The negative of that makes it 7. So that makes your neutral solution have a pH of 7. So the P function is always take the negative log, and it just makes numbers easier to deal with. but notice it's a logarithmic scale. So every time you change one pH unit, you change the concentration you're talking about by a factor of 10. So the hydronium ion concentration for lemon juice is approximately 0.0025 molar. What's the pH when the H3O plus concentration is that value? So you're going to take the negative log of that number, and that gives you the pH. So the pH will be negative or positive 2.60. We have a new rule for significant figures, and that is that you're going to have to the right of the decimal in your pH the number of sig figs that you had in the number for your concentration. So we had 2 sig figs, the 2,5. So we're going to have 2 digits to the right of the decimal. And then this 2 is considered an exact number. That's the log base 10 of our concentration. So we actually will go up a sig fig most times. So the 2 sig figs, 6 and 0 to the right of the decimal come from the fact that our concentration had 2 significant figures. So we're going to calculate the pH of an aqueous ammonia solution that has an OH minus concentration of 0.0019. So first we will use our Kw. So Kw divided by OH minus. Oops, they wrote that backwards. The minus should be on the other side of the 1. So if we go back and look, if we know the H3 plus concentration, then we can, or if we know the OH minus concentration, we can use it to calculate the H3O plus. So if we have a solution with an OH minus concentration of 0.0019, Kw divided by that number gives us the concentration of hydronium cations. So it'll be 5.3 times 10 to the minus 12. Then we can take the negative log of that number, and it also has 2 sig figs. So we're going to have 2 sig figs to the right of the decimal. The log is 11, so that's an exact number. So we actually went up 2 sig figs when we took the negative log of this number. So acid rain is a matter of serious concern because most species of fish die in waters having a pH lower than 4.5 to 5. Calculate the H3O plus in a lake that has a pH of 4.5. So remember, because we're doing a negative log, as the pH goes down, the hydronium ion concentration goes up. So we want to take the inverse function. So let's just go back to where they showed you this right here. So if the pH is the negative log of the hydronium ion concentration, then the hydronium ion concentration is the negative of that. So it would be take 10, raise it to the negative pH. So we'll take 4.5. We only have 1 sig fig to the right of the decimal. So when you take 10 to the negative 4.5, you get 3 times 10 to the minus 5. So in this case, going from pH to concentration, we're losing a sig fig. Okay, so an acid-base indicator. So this is just another concept we have to learn about. It's a substance that changes color at a specific pH or pH range. Indicators exhibit pH-dependent color changes because they're weak acids and have different colors in their acid or their conjugate base form. So as the pH changes, as we just saw, you'll have more either in the protonated state as an acid or the deprotonated state as a base. So probably in Chem 107, you used an indicator at some point in a titration. And so that's how it was working. It was a molecule that changes color, whether it has its proton on it or not. So this just shows you a picture of some of the different indicators that we use. I can't remember what we used in our lab in Chem 107, but a lot of you probably use phenolphthalein. It's a pretty pink color, changes pH at about, or changes color at about pH of 7. So about when you go from acid to base. So this isn't something you have to know, but it's just a good thing to understand. How would we know the pH of something? And oftentimes we know the pH by using an indicator. So the pH in solutions of strong acids and strong bases. So if we have a 0.025 molar solution of nitric acid, HNO3, that's a strong acid, which I would tell you. We know if we put it in water and we say it's a strong acid, that means every single HNO3 that we put in makes an H3O plus. And so because of that, what our starting concentration of nitric acid was is now equal to our concentration of H3O plus. So all we have to do is take the negative log of the concentration of the strong acid, and we get 1.60 for the pH of that strong acid. Notice it's a very small number. pH goes down, as I said, as the concentration of the acid goes up. Now, if we have a strong base, it's the same exact idea. If we say sodium hydroxide is a strong base, means it completely dissolves in water, and every sodium hydroxide that you had put in creates an OH minus. And so because of that, the OH minus concentration is equal to your starting sodium hydroxide concentration. If you want the pH, the first thing you have to do is get the H3O plus from the OH minus. So you take Kw, divide it by 0.025, the concentration of the OH minus, gives you the concentration of H3O plus. And then we are going to change that into a pH by taking the negative log. So the negative log gives us 12.40. So we're going to have 2 digits to the right of the decimal place because we had 2 significant digits in the concentration of H3O plus. Now, if we have weak acids, we're going to have to think about what we learned in the last chapter. So we're going to have to remember that it's an equilibrium. So when you draw the double arrow, that means some reactants remain and some products remain when things stop changing. And so if we wrote the equilibrium constant for this reaction, it would be hydronium ion concentration times the conjugate base of my acid divided by HA. Water is a liquid, so it wouldn't be in the equilibrium expression. So this is really just a K. We'll call it a Ka because it's for the acid dissociation of an acid. So it's just a specific name of a K, but it's just a K. So it's a K just like any K that we used in the last chapter. And you really wouldn't even have to know that this is an acid reaction in order to know that that's the equilibrium constant for it. So there are tables in the back of your book, a huge table that tells you the Ka for different for different acids. So the larger the Ka, the stronger the acid. So the larger the Ka, what we learned in our last chapter about equilibrium constants, mean you have more product. If you have more product, it's a stronger acid because you have more H3O plus. So as you look at these Kas, going from top to bottom, you go from stronger acid to weaker acid. And the top one is very strong, 2 million times more product than reactants, whereas at the bottom, methanol is really barely an acid at all. 2.9 times 10 to the minus 16 is the product over reactant ratio. So if we want to think about how we're going to use this, it's just exactly the same as the last chapter. So I really want to keep focusing on the idea that in this chapter, we're not introducing a new idea. Equilibrium is equilibrium. All we're doing is applying it to a special system, acids and bases. So in this case, it says we have a pH for a solution of HF, and that's not in here, but oh, yes, it is. It's the third one on the list. So it's a weak acid. Its Ka is 10 to the minus 4, but it's a relatively strong weak acid. So we have the pH, and they want us to calculate. Here comes my kitty behind me. His name is Tupai because he likes to turn circles. So what are the values of Ka and the pKa? So we have to introduce the idea of a pKa. So we have the same equilibrium expression. You put the HF, the weak acid, in water. you make hydronium and the conjugate base. So at the start, you start out with 0.250 molar HF, and you start out with 0 of the two products. And then as it goes to equilibrium, some of the acid dissociates, and every time an HF dissociates, you get an H3O plus, so you get negative X here, and positive X for the H3O plus, the hydronium, and positive X for F minus. And so we know that at equilibrium, the concentration should be 0.250 minus X, and then X and X for the products. But in this case, we know what X is. We don't have to solve for it. We know what X is because they gave us the pH. So if X is the hydronium ion concentration, we can get that by taking 10 to the minus pH. And so when I do that, I get the hydronium ion concentration to be 0.00920. And therefore, I can use that to get the Ka. So the hydronium ion concentration is going to be equal to the F minus concentration. So I have the hydronium ion concentration. I'll set it equal to F minus. And then HF is going to be equal to what I started with minus how much dissociates. So it will be equal to the 0.250 minus our X, 0.00920. So we're left with 0.241 molar at equilibrium. And then you can just put those into your equilibrium expression and solve for Ka, 3.51 times 10 to the minus 4. And a pKa is just a nice way to not work with those exponents. So just like you take the pH to get the pH, the negative log of the hydronium ion concentration to get the pH, a pKa is the negative log of your Ka value. So the negative log of 3.51 times 10 to the minus 4 gives us a Ka of 3.455. So if we want to calculate equilibrium concentrations in weak acids, it's exactly like the last problem, except now we're going to be given the Ka. So it asks us to calculate the pH. In this case, they gave us the pH, wanted us to get the Ka. Now they're going to give us the Ka and ask us to get the pH. So the reaction is HCN, which is a weak acid, and you'd know it's a weak acid because I'd give you a table and you'd find it in there. So our hydrocyanic acid is the second from the bottom. So we have a weak acid, react it with water, make hydronium and the conjugate base. So we start out with 0.10 molar of the weak acid, about 0 of the products. The reactant goes down, the products go up by the same amount. And now because we have the Ka, we can solve for X. So they gave us the Ka. But they didn't use the right Ka, right? So they tell us that the Ka is 1.4 times 10 to the minus 9. But then they use 4.9 times 10 to the minus 10. Is that out of the table? Yeah, so they just wrote it down wrong. That's not the right value. And this is the value out of the table, so that's their error. So don't be confused by that. So you can get the Ka out of the table, 4.9 times 10 to the minus 10. X squared over 0.10 minus X is our equilibrium expression. I can solve for X. And in this case, because the equilibrium constant is so small, it's 10 to the minus 10, that means really not much of it dissociates. So we're going to make the approximation to make this easier to solve. We're going to say if I subtract X from 0.10, and because it doesn't dissociate much, I'll still have about 0.10. We can check and make sure that's a true or an accurate approximation as we go through this calculation. So that allows us to say it's X squared over 0.1. Then that's really easy to do that math. You just multiply the Ka by 0.1 and take the square root. Would it be true that if X was 7 times 10 to the minus 6, it wouldn't change 0.10? Yeah, because within the number of sig figs we have, you'd be subtracting a number that was way, way, way past 0.10. So that was a good approximation, and that just made the math easier. And so now to calculate the pH, do exactly what we've been doing, negative log of hydronium, negative log of 7 times 10 to the minus 6, and the pH is 5.15. Okay, I think I'm going to take a break there and we'll finish the rest of this chapter in a second lecture.